Welcome to this inaugural NextCOMP annual lecture. For those who don't know me, I'm Professor Milo Schaffer from Imperial College. I'm the PI of NextCOMP, which is an EPSRC program grant developing a new generation of composite materials aiming to demonstrate the value of hierarchical design in the context of improved compression performance. The research program is a partnership between several different departments at Imperial College connected to the Composite Centre and the Bristol Composite Institute, as well as about 15 other partners from UK catapults and across the industrial supply chain. We also have a panel of exceptional international advisors who are kindly donating their expertise to the project. And we're delighted that Professor Véronique Michaud is on our board, and doubly delighted that she's agreed to give this lecture for us. So just a few words about her. She originally graduated engineering from the Ecole de Mines in Paris, received her PhD from MIT, and after periods of working at IMP Grenoble and the Ecole Centrale in Paris, she moved to EPFL in 1997, where she's now professor and head of the Laboratory of Processing Advanced Composites. And there she's pursued a range of research, much of which is relevant to NextCOMP, including the development of structured resins and then the transfer of new composite materials technology out of the lab and into commercial reality. So I'm very much looking forward to her talk, and thank you for joining us. I think you can post questions as we go along, and we'll come to maybe and have a little question answer session then. So Véronique, over to you. Thank you.
Okay, thank you very much. So thank you, Milo, for this kind introduction, and thank you all for being here today. Sorry, I'm not in presence at Imperial College. I wish I could, but that's the way we have to do now. So I will also, let's see if it works. Yes, this is my title. I just want to acknowledge also that it's not only my work, of course, but a bunch of other people, among which Amael Coad, Romain Triguera, Nathan Hostetler, and Cecilia Scazzoli, who've been very much involved in the work I will present. So before I start, because I know you all like to do some sports, we do some sports here with nice, beautiful hockey sticks that are made of composites. And most of the time, well, we suffer some issues that they actually break. Notice that I didn't put any soccer ball because I don't want to talk about the fact that Denmark lost yesterday to England. But anyway, so this is what happens, and we know all. I don't need to explain to you that composites are great. They are lightweight. They're made of fibers and resin. We get good properties, but they are prone to some cracking, maybe also micro cracks in the matrix, or maybe complete failure, which causes problems. And this is not only in sports, but it's also, of course, in very relevant automotive, aerospace, energy topics. And one big issue that we see with this is that, first of all, we generate a lot of waste. But before generating the waste, we also very often end up repairing composites. And that is also a very, very costly business. And it also leads to the question of sustainability and durability. Should we make the material more durable, more easy to repair? That would avoid a lot of waste and also improve their environmental footprint. So the current strategies for these things are typically inspection. So you have to send some guys up there on top of the windmill blades. It's also time consuming. You have to, of course, a downtime that is important. Then you can try to repair with some repair kits and so on. Or if it's something that like a hockey stick or a pair of ski, sometimes you would never repair, except in our lab we do this, but you would just throw them out. So this leads to long downtime, manual intervention, need of skilled people, or the part exchange. And for example, only in the windmill industry, the estimated cost of repair was about $13 billion in 2020, so it's not negligible really. And the market needs are really that we could repair on site or have a healing process. So some way that the material could repair itself without manual intervention. But this, of course, should be at a limited cost and also at limited loss in properties of the composite, of course, because it still has to be a structural material. And this is valid in many composite sectors. So you all know also, I think in this crowd, that there are some strategies to mitigate damage. And the current strategies are really often to limit the damage growth. So either you have to make sure your design is, of course, correct to avoid to have damage. But also if there is damage, for example, due to an impact, You can try to improve the intrinsic resistance to crack propagation by, for example, toughening the matrix, using thermoplastics instead of thermosets, and so on. But another way is also to say, well, we know there will be damage events. And if we have a method to localize the damage, to close the crack if we see cracks and heal the material, all this without compromising the structural integrity of the composite, it would be really, really great. So it's a bit the same as yourself. So if you have a wound on your skin, it will heal by itself. If the wound is a little bit too big, you might have to go to the doctor and get some sutures to close, but then it will also heal. And of course, there's a bit of a need of manual intervention here, but at least you don't need to change the part or your arm, for example, or your skin, and you can base yourself on this type of principle. So the idea that we were pursuing in the lab is to combine both two. So to have something that is still a decent composite with a decent matrix, because a lot of work done on self-healing always uses such a bad, composite, such a brittle matrix that nobody would ever use it in their right mind in industry. So we try to look at both worlds. So keep it tough, keep it quite, damage tolerant, but at the same time, make it healable so that we can also heal it if there is damage. So we're talking here about composites done mostly by infusion or impregnation, like we would do for wind turbine blades, for example, where we mix an epoxy with fibers to get a composite, or actually in the Prepreg form, it's okay. And this is just an example of the type of things that we were after, an example of delamination and micro cracking after a low energy damage event. This was done by some colleague a long time ago, but I like this picture because you really see that there's a network of micro cracks that was caused in the material. You barely see it actually from the outside, which is also one of the issues with carbon composites. They tend to delaminate easily, but we don't always know it. And so we are looking after these. So our initial approach was to say, okay, we can use a composite, traditional composite, but instead of having only an epoxy matrix, we use a thermoplastic healing agent inside the matrix. And the idea is that you have a crack, you have this fiber reinforcement bundles here, schematized, of course. And then in the resin-rich region, you have this mixture of epoxy and thermoplastic phase. So if you have a crack, by moderate heating, you, for example, at 150 degrees, then the thermoplastic phase should melt and fill the crack and help to solve this issue. Of course, there are many things that remain. The epoxy remains where it is, so the crack is mostly filled with a thermoplastic phase and so on, but this is the idea. So we started by working a lot on the model system, which is epoxy with polycaprolactone blends. We found in the literature that this was done before, and that was our inspiration, that, for example, in mixtures of epoxy and PCL, we could see from the literature that there is an interesting microstructure, and if you have a crack, and in that case, they heated it at 190 for 8 minutes, and you see that the thermoplastic has filled the crack. They also looked at the phenomena. They saw that it was a polymerization-induced phase separation, so PCL and epoxy mix in the liquid phase before, and then when the epoxy starts to react and polymerize, you have a very complex phase diagram taking place and a polymerization-induced phase separation. By looking at the content, increasing the content of PCL, they also found that you can cover a wide range of microstructures, from a microstructure that is mostly epoxy with a bit of balls of PCL in there, to a co-continuous microstructure, to microstructures with epoxy beads that are linked with PCL in between, and to very much PCL. And what they found in that work was that about 15 to 8% PCL was good for them. And they also saw that what was really interesting with the PCL is that you have a phase expansion that is quite good. So if you look at the volume difference when you pass here in the temperature, the melting point of the PCL, you see that the PCL tends to expand quite a lot, about 14%, and then it will start to bleed out. So you need this if you want to have enough bleeding. So we worked on these PCL blends and we decided to use them as a matrix for a composite. First step was, of course, to use it as a metric and see what it does. So we mix at 140 degrees, the PCL epoxy. Then we cure, we had a DDS hardener at the time. We cure 3 hours at 180, and we have indeed the phase separated structure that we were expecting. We looked at the properties. So this is the storage modulus of the pure mix blend at 25 and 150 degree. We see that, of course, the more PCL you add, the lower the modulus. But if you remain in a reasonable range, you still have a modulus that is about 1.5 gigapascal, which is kind of okay. And then at high temperature, of course, it decreases, but not to zero, which was the important thing. So the epoxy phase is interconnected enough that even at high temperature, when the PCL phase is molten, we still have, because at that temperature it's clearly molten, we still have a network, a skeleton that holds everything together. So we understood a bit how it works. We also looked at the toughness of these materials, and we saw that indeed from the epoxy to epoxy plus more and more PCL, we see that the toughness, K1C measured by TDCB in this case, decreases progressively. And when you get these PCL metrics with epoxy particles, you have quite a low toughness. But the healing efficiency, of course, does the contrary. At the beginning with pure epoxy or very little, you have no healing efficiency, and then it increases. And so it's the toughness recovery is almost complete when you have already maybe 25–30% of PCL in volume this time. So we also looked clearly that we still see the PCL melting transition. So it's really a phase, no miscibility of each phase. We can see the epoxy glass transition in that case. And we saw that we could actually heal and reheal several times the same TDCB samples. And we lost a bit of healing efficiency, but we actually, it can still be done several times. So this was in 2016, and okay, we were happy. We said, okay, let's try this in composites. So we use this as a matrix with fibers, and our goal was always to use composites that are, structural composites. So at least 50–55% of fibers, a real composite, I would say, not a fake composite with very little fibers. And the idea was to see if we have a crack. We can open, we did a lot of DCB tests. And then if you heat, you will close the crack again, maybe not fully, maybe you still have some locations that are not fully closed. We will see that later, but hopefully it should work. So first thing is to look what happens when you mix this Epoxy-PCL blend into twill glass fiber, which is the workhorse of cheap glass fiber that we use in our lab. We saw that, of course, there is a sizing that is an epoxy-based compatible sizing. So the epoxy phase tends to nucleate on the fibers, but the phase separation still takes place. We saw also that there is a bit of a change in the morphology of the phase separation due to the diffusion length between the fibers and so on, but it's still okay. And then with the DCB test, we saw that in terms of so the modulus of the stiffness of the first DCB curve, we had not much loss compared to pure epoxy. Of course, the fibers dominate. We had a full stiffness recovery for several damage and heal cycles. And we had, however, the energy release rate, so the G1C of the material was quite decreased compared to reference epoxy composites. It was 35% less than the normal epoxy. And we had a moderate toughness recovery, so due to this incomplete crack fill. But we had some healing efficiency in terms of the stiffness recovery in particular. It worked actually quite well. So we were fairly happy with this. We saw that there were some problems, but we managed to do some publication anyway. This was in 2017. So then we said, okay, because we have a hard time to fill the cracks, a DCB test, in fact, is not representative of what you have in real cases. In real cases, you have the wind turbine blade has an impact, and you want to heal after impact, so you don't need to fill the crack because the crack is very small. So we decided to do impact testing, and we used different impact. It was always between 20, 10, we went up to, I think, 40 joules. And after impact, we see that, of course, there is a big damage, and using glass fibers is great because you can see through. And then after healing, we see that, okay, at the impact of 20 joules, we have a reduction in the damage zone, but it's still visible. After 10 joules, we had a damage zone here, and after healing, we barely see the damage. So, of course, if we have broken fibers, we don't repair them, we repair only the matrix. We did a bit of C-scan. We see that after healing, so this is before and after healing, we have a good reduction of the size of the damage zone. And of course, we wanted to relate this to a mechanical test, and you all love compression in this crowd. So we also did compression, but mostly compression after impact as well, which is often used to test what happens after impact on the composite. And the force, so it's in actually the stress, the maximum stress of this compression after impact. If you have a plain composite that we made the same way, we had a value around here, so it decreases, of course, because of the damage after impact. If we took our composite, we saw that we have a reduction in initial properties. We knew it because the material is a bit weaker, and we had all the toughness issue. So we were here, but after healing, what we found, if it wants to hello, it's got. Yeah, we had this blue curve here, which shows that, okay, it's not as great as the plain material, but which was not great in that case, but we have a recovery. And we see that the healing efficiency in compression after impact is almost 100% compared to, we have almost the same value as the one without impact. So we recover the energy here. But then if we go a bit higher, then we lose, of course, because we start to damage the fibers. So we saw also that over multiple cycles, it was possible to heal. And we saw that at high energy, we had large crack, fiber breaks, so then we could not restore. But we still managed to do a publication on this. It was in 2017 again. Then we decided that, okay, the toughness issue is linked to the microstructure size. And we had discussions with our colleagues from Ghent University, Wim van Peppegem and Karin de Klerk. They've been working a lot on electrospun nanofibers, and they showed beautiful results at some conferences that with the nanofiber mats, you increase the toughness tremendously with these nanofibers. So we made a small collaboration with them and used electrospun PCL nanofibers, which they produced for us. We integrated them into the glass fiber fabric as an interlayer between the fabric. And then we wanted to see what happens. So there we used a resin with low viscosity, a room temperature infusion, because we didn't mix the PCL directly then into the mixture, but we had the PCL here and we infused with a pure resin. And we used the rim, which they used a lot in the lab. What we saw was very interesting. So if you look at the plate one is the pure epoxy reference rim plate. We had a G1C of about 1,000 and so on, which was moreover what we expected for this material. And we cured it at room temperature, which was the recommended cure for this resin. Then we did several plates with the interlayer of PCL, such that we had about 20% volume fraction of PCL in the epoxy phase, in the matrix phase. And then we did either a cure at room temperature, so exactly the same as plate one. So this is just the PCL, not molten, it's cured, and we have we see the effect. So indeed, we have a toughening, so it works. But then we also cured some plates at 60 and 80 degrees to see what happens if we actually melt. So we go over the melting temperature of the PCL. We should have a melting and a phase separation. And we saw that indeed we still had a very good toughness. So it works well. We looked at the microstructure, and this is an example of what it looks like. It was a bit messy, but if you look in more details, you see here that you have regions where you have an epoxy rich region with some PCL particles that you can see here. Some regions had a mix of epoxy and PCL intertwined domains. And by the way, you can see the PCL and the fracture surface is quite elongated, so it works, it does its job. And then some regions had the epoxy particles in PCL matrix, which is the microstructure that we like. So we see that we have different days, but we do have this phase separation kinetics taking place when we cure at 60 degrees and then 80 degrees for 15 hours to do the post-cure. So this is perfect and it works well. And we actually published all this also, this is in 2018. But what we saw, which was the downside of it, we have a great toughness. But then we said, okay, let's heal that composite. And 30 minutes at 150 did nothing to it. This is the DCB curve of before, the virgin composite, and then the DCB curve of after. And you see that normally we should expect to go up there again, but we were here, which means that we have zero healing efficiency. So we looked into why this is happening. If you are interested, you can read the paper we did on this. But we found that there are many different reasons. One of it is the stretched polymer fibers that you have in these nanofiber mats. When you heat them up, they are actually quite elongated. So they want to shrink back. And so instead of going out, they were actually shrinking back into their little holes. And so they were not at all going into the crack. Also, the viscosity of the PCL that we used for making these nanofibers was a bit high, so it wasn't really flowing, and in these narrow channels that we had. So we understood why, but at least it was not so great. So the next step was to say, okay, what can we do? And this was in 2018 or something. Amael progressed in his PhD thesis, and we said we have this situation. If we use nanofibers, we have a great toughness, but zero healing efficiency. We also tried, this is the baseline epoxy we had. So around here, we tried also PCL microparticles and whatever, and nothing worked in terms of healing. The only healing we could get was either with the blends, as we did, or with just taking PCL interlayers, so in between the composite. That was a great healing efficiency, of course, but zero interlaminar or very low interlaminar fracture toughness, because we really weakened the material. So how to get out of this line? We tried to see what we can do. One idea that we had, since we like to use shape memory alloys in our lab, was to put a bit of stitches across the composite. And so we took a sewing machine, and then we took 150 micron diameter shape memory alloy wires. We just stitched them through, and then we did some impact testing, recovery after impact, and so on, DCB. And we saw that indeed, in that case, you have a good toughness because the toughness is given by the SMA stitches that you have, and you also have a decent healing efficiency. And we also published this one, and that was in 2018. So what we see here, it's blocked. So 1 volume %, so it's not so much, and it can make sense. And if you see here, we see that we have, this is a DCB test. You see the stitches here are completely broken, of course, that's not the idea. But if you don't break, after damage, you see here you have a big crack. After healing, so the shape memory alloy wires, they actually heal the crack, so they help to close the crack, sorry. And then we see also that if you look at we had the SMA just at the end of the sample, and we had a virgin, without SMA zone here. And you see whether you have just a pure epoxy or Epoxy-PCL, you see that the fracture toughness with the Epoxy-PCL indeed is a bit lower, as we knew when you have no SMA phase. But as soon as you go into the region here where you have the SMA wires, we see that we have a big increase in the fracture toughness created, of course, by this. And we saw that also in compression in impact and compression, so the recovery area was quite good, and we had a good healing efficiency after that. But it increases the weight and the cost. So it's not, and it's a bit cumbersome to have to go and stitch, SMA, and they're quite expensive. So it's not really what we want to do. So with all this, we were in 2019 or end of 2018, Amael finished his PhD, and we were a bit stuck. We said, okay, nice thesis, nice work, but we don't really get what we want. And then we started to think, and we had some ideas of improving the matrix system. So I cannot really tell you what we did because it's still protected. We filed a patent, but it's based on our understanding, of course, of these 3 years of trying to reach the perfect material. And we found a system which had a good fracture toughness, higher than the baseline epoxy, and a good healing efficiency. And so based on this, we went on doing some tests. So we did some, and this was after Amael was finished with his PhD, and he stayed with us for 6 months. He was actually, the funny story was he was waiting to get a fellowship to go to Milo's lab and do an academic career, and first do a nice postdoc in Imperial College and so on. And then so we had a bit of time, and we were working on making some more papers and stuff and doing some tests. We saw that it actually worked well, our idea. And if you compare the healable system after impact, the reference is very much healed. Of course, the broken fibers still cannot be repaired, but we see also that the resin, if the reference is pure epoxy, has some relaxation also if you heat it up, but with damage, whereas with our system, we have the full healing. And then we also looked at the impact performance. The reference system after healing, 150 degrees again or something for a few minutes, it was healing a bit, but our system gave decent healing efficiency. And after up to 17 joules impact damage, which is okay. And then we also did a bit of aging performance. So we looked at what happens if you put this stuff in humidity at 80 degrees for some days. And then we saw that compared to the reference system, indeed, we absorb a tiny bit more water, but it's still manageable. We have a little bit of decay after SBS, so the toughness of the material after this aging, but not that so much more worse than epoxy. And then we also did some fatigue. And then by then, I should say, I might have decided not to do a postdoc and to stay and make a startup company and really go into trying to bridge and get this material into application. So we did some fatigue performance. We saw that compared to the reference system, this is all normalized to 50%, because our system was a bit less than 50% at the time. But we see that the healable system has a little bit lower properties at low number of cycles, but actually crosses over, and our high cycle fatigue was actually quite comparable, even better than reference epoxy. And then we decided to do some healing cycles. For this, we had to do quite a bit of work to try to model the probability of survival and say, we want to do the healing cycle when we are at maybe 90% probability of survival of our part. So for this, what we did is to say, okay, for the healable and for the reference system, if I want, for example, 80% probability of survival, and I'm at 320 megapascal amplitude, then I have to go here. And then if I go here, I know that I should stop after this amount of cycles. And if I'm at, for example, 250 and I want 80%, then I know I can go to up to 10 to the 4 cycles. So this gives me some kind of idea to say, okay, I have a part, it's running, but I know after so many cycles, I should stop and do a healing step. And then I can make it go again. So it's a maintenance schedule kind of approach. So we decided to do it at 90% survival rate. And what we found is that the reference system is below. We see that we go to this number of cycles for 90% survival rate. And then we say, okay, let's put it at 150 degrees in the oven for 30 minutes. And then we bring it back. And then we do it again. And then after the second round, it actually failed. Whereas with the healable system, we put it in, we stop it, we heal it, we put it back in, we run, we stop, we heal, we run, we stop, we heal. And we did it up to 10 times, and then we got tired, we decided this was enough. But we had like an infinite lifetime, at least, by performing this 30 minutes intervention every, so many cycles. So we saw that this was quite promising. And then we went on, we also did some prototypes, and by then Amael was here, we had Nathan, who's now doing actually PhD McGill, and me, we're all very happy. We made some nice prototypes. We decided to give a name to the company and so on. And at that time, it was still not fully a company, but it was in the lab. And we made an aerospace kind of a nose cone part. that look very pretty. Our cleaning lady, she always thought it was a lampshade, but in fact, she was quite right, because this part, which was actually bumped and healed many times, recently in June 2021 was at the Vivatech show in Paris. And you see it was used as a lampshade. And you should see here, the person who's looking at it, very interestingly here, you can recognize Emmanuel Macron, the president of France. So we're very proud that, our beautiful homemade demonstrator went up to the eyes of the president of France. So then you get to see it as well, not only the president of France. So this is the video to show how we do it. So we have a big bowl here, 1.5 kilograms, that is impacted from quite high. Then we see the impact damage is here. We heal it for 1 minute with a heat gun, and the impact disappears at about 150 degrees. And we recover the initial mechanical properties by compression after impact. And so this part we've used a lot, and it's been impacted many, many times, and it still looks quite okay, I must say. So we're very happy about this. We went on and made many more demonstrators. We made skateboards with carbon fiber. We also made some demonstrators with flax. I think this one was made with flax fibers as well. We also made a surfboard because one of the guys who actually is now a co-founder of the company, Robin, is here. So he absolutely wanted to try to surf on the surfboard made with our material. And see, we have even a video that shows that you can heat it up with a hair dryer of Amael's girlfriend, and everything worked fine. So with that, we moved to this company that was created in January 2020. And the idea there was to go not for infusion and so on, but to go for prepregs, which was an easier system to start entering the market, because a prepreg is a prepreg, and it's a, you can just buy it. And the idea is to have a prepreg that has decent properties, but that you can repair quite easily, that can regenerate many times. And at the same time, the matrix is such, or the material is such that on normal use, you have a quite good toughness also of the material, so a quite good damage tolerance. And it's compatible with normal manufacturing techniques, so you just take a prepreg that you can try. And then it's also has a potential for improved recycling. I will not talk too much about it, but we have a project running on this side. So we went on, we had a trademark HealTech for this prepreg. We had different possibilities, one with carbon, one with glass, now that we have. We got a lot of, or they, I should say, got a lot of recognition, or we first got a lot of grants to help develop this. And also then some kind of prizes, the JEC World recently, and then some all kinds of innovation award, and also circular economy type of awards like the Solar Impulse Efficient Solution, because we have, we believe, possibility to think a bit circular in the composites industry with our material. The idea being that if you have damage to the matrix in your part, then you can just heal and use again, and then maybe you will have a damage again, but you can heal and use. So you can follow this route. Now, of course, if suddenly you have a damage that is going to the fibers and we cannot really repair or not repair enough, then we have a route to recycle the material. And it turns out that with our special metrics, we are working on this right now on the project, we have a somewhat better recyclability than with the current normal epoxy composites. So it's also a way to recover the material a bit better, and we are trying to think how to do it best to reproduce then materials, reuse, and then maybe we can re-inject it into another part, but at least avoid to have to throw away and landfill or burn the material without trying to exploit the maximum out of it. So before I finish, there was a question by Milo on how do I view this as an academic who ended up being co-founder of a startup company. And if you had asked me, I think 10 years ago, I would have said, well, it's impossible to do a startup with on composites, because people who do startups, they are doing apps for the telephone or stuff like that. But making composites requires machines, requires equipment, requires a lot of investment. And you cannot just go ahead and say, I will start build a line and so on. So since then, I learned a lot. I learned a lot actually from also the startup of that BComp that you heard about. It was made by two people who were actually PhD students in our lab, Christian and Julien. And their startup now has 10 years, just celebrated their 10 years, and they're doing quite well. So I discussing with Christian, I learned a lot on the fact that we can think about starting a company in the composite field. And then, of course, what's important is to have a super motivated team, because me alone would have never made a company. So you need to have motivated people who are really ready to jump and carry the load and do all the work, and because it's a tremendous amount of work. Before we started, I also checked the craziness of the idea. So with exactly the same guy, Christian, a next PhD student, we went through this process, and we had dinner with him and with Amael, and we asked him, we showed him the idea we had, and he said that indeed we are crazy, but we should go ahead. And he's actually so interested that he's been really helping us, giving a lot of tips, a lot of pitfalls to avoid, a lot of good advice on things to do and things not to do. So I'm really grateful to him, because he really made me at least feel a bit safer that we were not completely crazy. Then we also have to have a good startup ecosystem. I think in UK, you have a very good startup ecosystem. So I think you are in good hands. I know actually one of my ex-PhD students is also at Imperial, I think she's still there, Eva, working on the startup ecosystem. So you're in good hands. And then we also had a good ecosystem in the Vaud and Canton and the Swiss community. So really, we got a lot of money to do the translational project to bridge the gap between the EPFL thesis result and the product. And so for a year and a half, we really got funding to be able to fund Amael and some of his colleagues to do a lot of testing and to really start hitting the ground running for the company instead of having it, just like that. And then there was a transition period where the company, of course, starting a company just before COVID is not such a good idea, so we were a bit delayed. So we kept the company hosted in our lab for a bit longer than we wanted to, but now they are completely spun out. I realized so that you can start with minimal infrastructure. The trick, for those of you who don't know, is to make a partnership with companies that are producing, so you can actually subcontract a lot of things. It's a bit risky because, of course, you need to be, a good client and have a good relationship with the subcontractors, and that they don't put you behind all their other bigger clients. But if you find a good partners, you can actually produce your material and subcontract. So you don't need to invest in a lot of stuff. You just need to invest in minimal equipment, and then you can start already like that to sell materials. Of course, you have to use your useful prior experience in whatever happens. And so if you have kids, don't be shy to go in the parents association. They always need parents in the daycare associations. At least in my case, I was very involved. I ended up running a small business with 20 employees and £1 million francs turnover, which was the daycare of my kids. And I must say, I learned a lot on the Vaud Canton rules, on businesses, and also on the risk that you have when you have a business with many employees and you need to get the money in, so that you can pay the salaries the next month. So it gave me also a bit of background, but also a bit of, being less worried about what can happen. And then the final point I wanted to mention, which is one I think is super important for academics. We have lots of discussions on this at EPFL these days, is to clearly define the role of the professor, so me, with the company. And at least at EPFL, it's very, and in the Swiss ecosystem, you have to really set very clear relations between the lab and the company to avoid conflicts of interest, favoritism, and things like that. So there's no way companies can be hosted in the lab forever and use, the taxpayers' money to actually run their company. So you have to do very clear IP agreements. you have to do a very clear relation. So if the company comes and uses some things in your lab, they have to pay per hour, the same way other companies coming into our lab pay per hour if they want to do some stuff. So you have to really be very clear as possible and as straight as possible to avoid any problem. At the same time, I had to define what is my role. So, and it's now becoming clearer with the time, is really a role of scientific advisor. So I'm here to, of course, I'm happy to see the things going on. I'm not at all involved in the company running the business, you know, all these decisions that they take, the board, I'm not at all in there. I let them run their company, but I'm still, of course, interested because I'm a co-founder and I like the idea. So I try to keep an eye, but a very scientific eye. And the main goal for me is to keep the pipeline fed so that I can continue to run projects on these lines. And we have some projects now that are in collaboration with the company to look, for example, at the recycling and so on. So research projects, and I treat them like any other company to some extent, but I feel happy that we can continue to collaborate. And this takes some time to really find what is your position. You should not really tell them what they should do. You have to step back, but you have to keep the scientific view on it. At least that's my view. So to conclude, I hope that you know that composite matrix is now based on thermoset thermoplastic blends. So and the model system that we worked a lot and we continue to work a lot as a kind of workhorse that we can publish on is epoxy and PCL. Phase separated blends, it has a good potential for heat assisted repair thanks to this interesting interconnected microstructure and the fact that the polymer can heal, of course. Integration of SMS stitches has a really interesting aspect. It increases the composite toughness, ability to close cracks, but of course it adds weight and cost. So there could be other alternatives also of shape memory polymers, for example, we could think of using. They're not as strong, but they can also bring interesting options. We have a novel matrix material. Now we find a way to retain toughness, ability to repair, and a strong potential for recycling. And then I think in this crowd, you all know that bio-inspired and hierarchical approach seems to be a good inspiration indeed. So I think with all your inspiration that you have in this NextCOMP project, you're also in a very good way to get interesting results that potentially would be very useful for industry. So I have to acknowledge the funding. So all these PhD theses that I did over the years on self-healing were funded mostly by the Swiss National Science Foundation. We got more recently for an Inno grant, Venture Kick, Inno Booster grants from the Gebert Ruf Stiftung that was really for the translational research. Now we still have a grant from Inno Swiss collaborative with the company, and also Switzerland Innovation Tech for Impact Initiative on the recycling side. I have a lot of students and colleagues who helped us, especially a lot of students with master thesis and all. And this was a master thesis student who now is working as a researcher in the company. These are the people of the company, and this is the co-founders. So, and of course the compare team is heavy. So with this, I will be open for questions.